I'm Kasey Gandy. I'm a driver at Station 22 on the southeast side. I've been on a job for 19 years and just really like helping out with the paddle program. All right, so this is the hydraulics portion of your paddle class. We've got a lot of formulas you need to memorize for state test purposes. As an engineer on the Fort Worth Fire Department, your primary goal is to get your crew to the scene safely and effectively. And then at that point on a fire scene is to supply your nozzles with the appropriate pressure in order to get the appropriate nozzle reaction and provide the appropriate gallons per minute for that particular line and or master stream. So in order to do that, there's a lot of theoretical equations you're not going to use on the fire ground. That's why we have these pump charts for you. But for state test purposes, we need to know how to figure these formulas out. And it'll also make more sense where the numbers came from on the pump chart. In order to do this, our initial overriding formula is going to be our pump discharge formula. And pump discharge meaning what you're going to set your throttle to for that specific line. And in order to figure that out, it's going to be PDP is equal to the nozzle pressure plus the friction loss plus or minus elevation gain or loss plus your appliance loss. Okay. So in breaking this formula down, in order to determine your actual pump discharge pressure, a good starting point is going to be your nozzle pressure. Your nozzle pressure is going to be determined by what type of nozzle you've got. So for any smoothbore nozzle, you're going to use 50 psi as the value for that. For any master stream nozzle, you're going to use 80 psi. As far as state testing purposes go, if they ask you for a fog nozzle, your value is going to be 100 psi. Just know that in the real world, we use low pressure fog nozzles in Fort Worth, so our fog nozzles are going to be 50 psi. So whether you use fog nozzles or smoothbore nozzles in the city of Fort Worth, it's going to be 50 psi is going to be your nozzle pressure value. So that's a good starting point. It's going to be determined based on this. Then we're going to figure our friction loss out, which is essentially the loss of pressure as water moves through a pipe or a conduit. And this is where a lot of people get hung up. So in order to determine our friction loss, we got to come here to our friction loss formula, another formula you need to memorize. Friction loss is going to be CQ2L. And in this formula, the C is going to be a coefficient. And all a coefficient is a specific number assigned to a specific hose line by the manufacturer. All of our state testing questions and any questions you get on your homework are going to be based on these old hose coefficients. You definitely need to memorize these because they may or may not show up on your state test. Sometimes they give them to you, sometimes they don't. So definitely memorize these. But it's going to be a predetermined value. So it's not something you need to figure out, you just need to have it memorized. For example, if the question asked is using 1 3/4 line for C, you're going to use 15.5 as that value. If it's 2.5 inch line, you're going to use 2 as your C value. So it's predetermined, but you have to have that memorized. Our Q2, our Q in this formula is going to be our gallons per minute divided by 100. So if the question involves 1 3/4 line, we know that's going to be 175 gallons per minute. So what you do is you're going to put 175 divided by 100. It's going to equal 1.75. Very, very basic. Just make sure you don't forget to square that. So in that scenario, it would be 1.75 squared. So 1.75 times 1.75. And the last value in our equation is going to be the L. And that's going to be essentially just the length divided by 100. So our standard 1 3/4 cross lays are 150 feet. So you would put 150 divided by 100. It's going to be 1.5. So in that scenario, you would essentially just plug in the values here. Make sure you square your Q before anything else, and then go ahead and multiply those out, and that's going to give you your friction loss. Fairly uncomplicated when you're using fog nozzles because you know exactly what your gallons per minute is going to be. Now, they could throw you a loop and give you a smoothbore diameter of a nozzle, and then in that case, you don't know what your gallons per minute is going to be unless you use this third formula, which you also need to memorize, which is going to be your smoothbore gallons per minute formula. So in order to determine the gallons per minute flowing from a particular smoothbore nozzle, we need to use this formula. which is going to be 29.7 times d squared, which is the diameter squared of your tip, times the square root of the nozzle pressure. Plug those numbers in here, and essentially that's going to give you your Q for this formula. So it's one extra step you have to take in order to figure your friction loss for smoothbore lines. Don't get confused by that. It's just that extra step. If you can't figure out the gallons per minute, it's probably because they're throwing you a smoothbore tip size, and you've got to figure that out before you plug that into the Q. For our third piece here is going to be plus or minus our elevation gain or loss. So anytime you gain or lose, you're going to add or subtract accordingly. If your nozzle is going up 10 feet, you're going to add 5 psi for every 10 feet you go up. So for example, if you've got an aerial device that's set to 30 feet, then you're going to add an additional 15 psi just for that elevation gain. If your nozzle is going down a steep hill 30 feet, then you want to subtract 15 psi from that. Pretty simple there. Our last piece in figuring our pump discharge formula is going to be our appliance friction loss. And we've got a few tricky rules on that. You are only going to add your appliance friction loss if your flow is greater than 350 gallons per minute. So if on the state test they give you a question and your total gallons per minute flow is only 300 gallons per minute, disregard the appliance friction loss. They're trying to trick you. If it's 500 gallons per minute, then of course you're going to add it. Anything above 350, add that appliance friction loss. Your hose appliances are going to add 10 psi, only if it's 350 or above on your total flow. And any master stream device, you're going to add 25 psi. So as an example, if we're flowing our deck gun, that's going to be a master stream device. So our nozzle pressure is going to be 80 psi. That's a good starting point. And it's also a master stream device that's going to be flowing more than 350 gallons per minute. So you'll add 80 and then to 25 here for your master stream device. So we always flow our deck guns at 105 psi. Kind of illustrates that point. When we're figuring our friction loss for supply lines, so bigger lines, 3, 4, 5 inch line, they may ask you about the condensed Q formula. It's actually very, very similar to this. It's a shortcut to this, hence the condensed. It's not going to get you the exact result is plugging in your numbers into this formula, but it's going to get you in the ballpark very, very close. And it's a lot easier formula. All it is on a 3 inch, you're going to do your Q squared. So your gallons per minute essentially divided by 100 squared. 4 inches Q squared divided by 5. And 5 inches Q squared divided by 15. So have these memorized also. I know that some of these questions were on the last test as well. 2 more, and probably the most difficult to memorize of these formulas are going to be the nozzle reaction formulas. So in order to figure your nozzle reaction for a smoothbore, you're going to take 1.57 times the diameter squared times the nozzle pressure. And make sure you note there's no square root of the nozzle pressure on this one. For fog nozzles, probably the most confusing of all the formulas, your nozzle reaction is going to be 0.0505 times Q, not Q squared, times the square root of the nozzle pressure. So this one seems to be the most confusing, but it's just one of those things you're going to have to memorize that. So make sure you memorize pump discharge formula, the friction loss formula, your smoothbore gallons per minute formula, your hose coefficients, your rules on hose appliances, condensed Q formulas, and your nozzle reaction formulas for state test purposes. So when we talk about pumping proper pressures, we have a lot of guys that say, well, just who cares, just pump 150 on old hose that's supposed to be pumped 120. Okay, we've done that in the past, and it's fine. But we're going through this class in order to be better drivers, we're professionals, to be dialed in. I want my guys to go in and have fun and be as efficient as possible, and I want to provide them with the appropriate gallons per minute while they're having the most manageable hose line pressures. So some guys that put this class together initially went out and did some testing on old hose using our 1 3/4 150-foot booster sections. So the appropriate pressure for that is going to be 120 psi. When they did the test, They came out, the nozzle pressure of that was 50 PSI, which is what that nozzle is designed for. The nozzle reaction was 60 PSI. And NFPA says one person, essentially a one-person load nozzle reaction that's manageable by one person is 65 PSI or below. So that fits below that requirement. And our gallons per minute we were getting out of that was 175 gallons per minute, which is what that nozzle's rated at. So nice, clean results here. When you kick it up just 30 pounds to 150, you wouldn't think it would make that big of a difference. But what happened during the testing was the nozzle pressure kicked up to 80, so 30 pounds more than what it was designed for. Your nozzle reaction doubled. So you're working twice as hard on that nozzle reaction, and your gallons per minute went from 175 to 210. So roughly a red line's worth more of water. To me, doubling your nozzle reaction to get roughly 35 more gallons per minute doesn't make any sense at all. It isn't worth it. So can guys handle this? Absolutely. We got plenty of people that can handle this, but why? They're not getting much more water, and they're having to work a lot harder in order to work that nozzle through the fire. So, all right, so in figuring our master streams gallons per minute, we have a nice chart here that can help you out. You're gonna have to reference in some of your real world scenarios. That's the easiest way to do it. However, there is a nice trick here. If you look at this chart here, we'll have that out for you. Starting at 1 inch, it's tip, you're gonna have 200 gallons per minute. All the way up to a 2-inch tip, you're gonna have 1,000 gallons per minute. So for every 1/8 of an inch, it's called the rule of eighths, you come up, you're gonna basically essentially come up 100. So from 1 1/4 to 1 3/8, you come up 100. From 1 3/8 to 1 1/2, you come up 100. We should start with an 1 3/8 tip on our deck guns in the city of Fort Worth, because we are flowing 500 gallons per minute there, roughly 501. And the reason is that's our tank to pump limit. So our tank to pump valves are rated at 500 gallons per minute. So for example, if you've got an 1 3/4 tip here and you're running tank water and you're trying to flow 800 gallons per minute, but you can only flow 500, you're gonna possibly cavitate your pump. So that's why we always start with 1 3/8 tip. Any of your scenarios, you need to make sure, get up there as a driver and make sure you got an 1 3/8 tip on there. Once you establish a supply line, then of course you can move to a much bigger tip size depending on how much water you have. But always start on tank water with an 1 3/8 or less. 1 3/8 is ideal. We're gonna talk about the concept of constant pressure pumping. Essentially, all constant pressure pumping is you're gonna pull on seam, and you're gonna have a specific pressure that's higher than your highest pressure that you set your preset to. For example, if you're running old hose and your 2-inch is 150 PSI, then 160, 165, somewhere around there is a great starting point to have your preset set at. And the reason you wanna do that is you pull on seam, you can set your preset to higher than the highest pressure of your highest pressure line. And once you're done there, you're not gonna have to mess with any of your pressures with the throttle. That company's gonna pull a line, and then you can just basically gate each discharge to the correct discharge pressure as you open it using the gate valve. On the Pierces, it's very, very easy because you've got everything on one panel. On the older engines, you're gonna have to work the wheel valves a little bit more. It's gonna take a little more finesse. But once you get that line set, when it's flowing, water has to be flowing in order to set those discharge pressures. But once it's set, it's set. So another company can come, pull another separate hose line of a different diameter, and you can dial them in once they're flowing water, and you're not touching that throttle at all. Makes it very easy. You'll see in this class, we're gonna use it many, many times, and you'll actually get to see it in action, but it allows for some troubleshooting. And it also reduces the load on the engineer. So you're not having to run around back and forth, constantly tweak lines. It's much harder to do once you get more than two hand lines going, to be constantly tweaking those pressures. It'll make a lot more sense when we do it in person, and I think you guys will like it. It makes things a lot easier. You just have to have that plan, and you need to actually have to work with your crew beforehand to either preset your pressures. Like at our station, we have pre-flowed our lines with our preset, so we know I can drop they can open that line. They don't even have to be flowing. I can drop that valve down to a specific spot that I have marked, and that's going to give them the appropriate pressure for that line. And or those guys need to be flowing water for you to set the appropriate pressure. And you guys will get plenty of chances to practice that. Another really useful skill we're going to address in this class is our estimating additional water chart. What this is going to allow us to do is, on scene, especially something like an apartment fire, a commercial fire, where you're going to be using multiple lines, supplying aerials, supplying master stream devices, using a large volume of water, you're going to be able to have a really good idea of how much extra water you can get out of the plug. So if the chief comes and says, you're already flowing multiple hand lines and a deck gun and a blitz fire, and the chief comes and says, can I get one more line, or can we supply an aerial? You won't just be scratching your head. You can say, yes, sir, I can. No, sir, I can't. And then basically go from there to figure out what you need to do in order to achieve that goal. So in order to figure this out, and we'll talk about this in the actual class, requires 3 pieces of information. Number 1 is going to be your static pressure. Your static pressure is going to be your intake pressure when water is not moving or flowing. The second piece is going to be your residual pressure, and that's going to be your intake pressure once water is flowing. So you'll have your static pressure, it'll be set, and then once that drops, once the water starts flowing, that intake pressure is going to drop, and whatever you're sitting at there is going to be your residual. And the third piece is going to be your gallons per minute flowing. So that's going to be the amount of water that you're actually flowing at that given time. So obviously remember that this is dynamic. This is constantly changing based on opening and closing lines. So your static is going to be the same no matter what. Once you get your original static, your static stays the same. Your residual pressure is going to fluctuate based on you opening and closing lines, and also your gallons per minute flowing. So anytime you open or close lines, you're going to either be flowing more or less gallons per minute, and that's going to change your residual, depending on how many gallons per minute you're flowing. So anytime you want to figure this, you can take a picture. You know exactly what your static's going to be. Look at your residual pressure, figure out your lines and what you're flowing at that time, and then that way you can consult the chart here and use this nice chart to help figure out where you're going to flow. As an example, if your static pressure is 60 initially, and you open up a booster at 175 gallons per minute, and you open up a 2-inch at 250 gallons per minute, your total gallons per minute at that point is going to be 425. If you look up, and at that point you're flowing 425, your static was 60, and you drop down to 50 psi, you look up at your intake, and now it's at 50 while flowing 425, you can come down here and see that you can get 2 more times your current gallons per minute. So that means you're flowing 425. That means you can get another 850 gallons per minute on top of the 425 that you're actually flowing. And so essentially you can get 1,275 gallons per minute total flow at that point. You'll get a lot of chances to practice with this chart, but just you need to be familiar with it and understand, before anything, you need to understand the 3 pieces of information that you need in order to figure this out. Pump capacity versus capability. Fort Worth Fire Department engines are rated at 1,500 gallons per minute. Now, that's 1,500 gallons per minute at a draft that they do testing initially when they test these trucks. That doesn't mean that 1,500 gallons per minute is all you can flow out of these engines. In fact, you'll flow close to 2,000 or more in some of these scenarios, possibly depending on the hydrant that day. That's just how they rate it at a draft. So don't think that you can only get 1,500 gallons per minute out of your engine. We'll address the term running away, which essentially just means, you hear the term running away, it's kind of a slang, for your pump running away from the water. And essentially what that means is you're trying to pump more water than you have, than your supply. And this could lead to cavitation, so we definitely want to avoid that. RPM versus pressure mode. If you look on your pump boss panel, there's a mode button. Most of the time, you're going to be operating in pressure mode. So anytime you pull up and you're pulling lines off your truck and you're going to be the manifold pumper, you want to be operating in pressure mode. That's what the engine is preset to, so you don't need to do anything. Now, RPM mode is going to come into play anytime you're a pumper supplying a manifold. You're going to want to switch that over to RPM mode, and that's going to include anything like a reverse lay, relay pump, and or maybe even supplying an aerial, depending on if you're going to use their pump or your pump. All you need to do that is go to that mode button and hold it down for 3 to 5 seconds, and it will kick over from pressure to RPM mode. What this does is it eliminates the pumps working against each other. You want the pump at the manifold in pressure mode, and that essentially is going to keep those lines at a specific pressure. Once you kick over here to RPM mode as a supply pumper, what that's going to do is keep you at a specific RPM versus the two pressure, both in pressure mode, they'll be fighting each other. So don't forget to do that. Even if you forget to do this, at any point, you can hold down that mode button for 3 to 5 seconds, and it'll kick you over to RPM mode, and it'll make for a lot more smoother pumping experience. Forward versus reverse lays. We'll talk about some pros and cons. We're a forward lay department. It's essentially what we've done since I've been on. We're getting better at reverse laying, but forward lay is very simple. You're going to stop at a plug, you're going to drop your firefighters off, they're going to hook up, and then you're going to take off and lay that line down into the manifold engine. Pull off that line, hook into them, they've got water. Reverse lay, you're going to, instead of stopping at the plug, you're going to stop at the manifold engine, pull it off, give that line to the driver, and or put it under their tire. Then the driver can drop off his crew and then move towards the plug by himself, and then basically hook up to the plug down there by himself. Now, to me, the benefit of doing a reverse lay is, A, you get your crew to the fire, so they actually get to go play. B, you're relieving some seam congestion. You're going to get your engine out of the way. And then C, you've got your engine set up down at the plug, and you can do a volume connection. Basically you've got some more control over what's going on, and you'll have your engine down there as a pump if you need it. Who gets the static pressure? This is kind of a confusing topic. When you do a forward lay and your line goes into the intake side of that manifold pumper directly from the hydrant, once he opens up his intake and he's getting that hydrant water, that manifold pumper is getting the initial static. That water is going straight from the hydrant into his intake. If you do a reverse lay, it's going to be the opposite. You're going to drop your supply line to the manifold pumper, drive down to the plug, and essentially you're going to hook your pumper in between the manifold pumper and the hydrant. So essentially, you're getting that supply line into your intake at the hydrant first before that guy is. So when you do a reverse lay, it's going to be that guy that reverses out that gets the actual static. It gets a little more confusing when we do a forward lay. So essentially, we do a forward lay, and that they charge the hydrant. You open up your intake as the manifold pumper. You're going to get the static from the start. Now, once somebody goes back to boost your hydrant, they're going to tie into your system. So they're putting their apparatus in between you and the hydrant, and at that point, now they're taking the water into their intake. So although the initial manifold engine will get the static, the guy that's down there tying into the system is going to be the one that gets the residual. And you'll get to see this more in practice. It'll make more sense once we do it, but it does get a little confusing. On a reverse lay, you do not need the HUMAT, and we'll get plenty of chances to practice. On a reverse lay, you're going to drop your line to the manifold pumper, move down to the hydrant, position yourself, and at that point, you're going to pull off that supply line, hook it to your discharge, open that up, let them know you're getting tank water, and what you're going to do is you're going to have that gate valve on one side of the hydrant, and you're going to have the adapter, 4-inch threaded to 4-inch Storts adapter, or 5-inch depending on what you're using. And you're going to run a line directly, run a pigtail directly from that steamer into your intake. So there's no point of having a HUMAT on when you're reverse laying, because you are down there, you've got a pump down there. That pump is essentially your HUMAT. Anytime you forward lay, we want to use the HUMAT and the gate valve. And the reason being is if it is a low flow hydrant, either from a pressure standpoint or a volume standpoint, we cannot go back and tie into the system without shutting it down unless that HUMAT and the gate valve are on there. And you guys will see why it makes more sense in practice. Do we need it on every fire? Absolutely not. But when you do need it, it's just one extra step that doesn't take much time at all to have it all on there, and it's easy to tie in. Okay. All right, so in discussing static and residual, it can be kind of a confusing concept, so we're going to illustrate on the board here. Let's say engine 3's on, engine 22's on, fighting fire. Engine 3 is going to lay them a line, doing a forward lay. Engine 3 brings the line to engine 22, pulls on past, they're over here. At this point, the first person to touch water, a good way to think about this is whoever touches water first is going to get the static. So engine 22 is fighting fire here. They got a couple lines off. Engine 3 brought them a line, forward lay. At this point, they're going to charge the plug. Engine 22's intake is going to kick up, and so they're touching water first. Water is going into their intake first. So they're going to have the static. And at this point, if nothing else changes, engine 22, while flowing water, they're also going to have the residual because nobody else is tying into the system. Standard house fire, this is usually how it works. You just do a forward lay. You don't need to boost the hydrant. Engine 22 is going to have the static as well as the residual because they're going to have that initial static, and then as they open lines, that pressure is going to drop on their intake, and that's the residual. So that's the simplest of scenarios. In the opposite scenario, let's say engine 22 is on fighting fire. Engine 3 is coming along, and they're going to reverse lay to engine 22 because they come from the opposite side of the plug. So they stop here. They drop the line to engine 22, and then they stop at the plug and tie in. At this point, let's go back to our rule of whoever touches water first. So engine 3 is the first one to get water from the hydrant into their intake. So therefore, they are getting the initial static pressure. At the same time, they're in the system here, in between engine 22 and the plug. So they are also going to have the residual pressure. Anytime engine 22 opens up more lines, it's going to drop engine 3's initial static pressure, which is going to be their residual, right? So that's also an easy concept to remember. They're going to have the static and the residual. The most complicated scenario is a forward lay. So let's say engine 3 does a forward lay. And at this point, engine 22 touches water first. They get the water from the plug to their intake first. So they've got the static. Everything's going fine, and they realize they need a boost or a volume connection. So they command calls for somebody to go back and tie into the plug to boost the hydrant and give them a volume connection. At that point, engine 4 goes back and ties in to the plug via the HUMAT and the gate valve. So essentially, they are inserting themselves into the system in between engine 22 and the plug. So at this point, now engine 4 has the residual. So initial line was laid, and at that point, before anybody inserted themselves into the system, engine 22 had the static, and while they're flowing water, they've got the residual. Anytime somebody goes in to boost the plug and or just tying into the system, they are going to assume the residual at that point. I know it's confusing. It's going to make more sense once you do it.